The most dangerous stuff in the universe, strange stars. The universe is filled with exotic and extreme objects that challenge our understanding of physics. Among these, one of the most dangerous and mind-bending phenomena is the concept of strange stars, hypothetical objects made up of a substance so bizarre and potentially destructive that they could threaten entire planets and even other stars. Peculiar stars, composed of what's known as strange matter, represent a fascinating frontier in astrophysics, posing questions about the very building blocks of matter and the limits of what we know about the cosmos. What are strange stars? Strange stars are a theoretical type of compact star, similar to neutron stars, but with a crucial difference. While neutron stars are incredibly dense objects formed after a supernova, where protons and electrons merge to create a soup of neutrons, strange stars are composed of something even more exotic, peculiar matter. Strange matter is a hypothetical form of quark matter. Quarks are the fundamental building blocks of protons and neutrons, and they come in different flavors, such as up, down, and strange. Under extreme pressures, like those found inside neutron stars, it's theorized that neutrons can break down into their constituent quarks, forming a soup of quarks. If conditions are right, this quark matter could stabilize into strange matter, a form of matter that includes strange quarks alongside the usual up and down quarks. In a strange star, the entire object is thought to be made of strange quark matter, making it denser and more stable than a neutron star. This stability, however, comes with a terrifying caveat. If strange matter comes into contact with regular matter, it might trigger a chain reaction that converts the normal matter into strange matter. Strange stars are theoretical stars of strange quark matter, a more stable and denser form of matter than the neutrons found in neutron stars. Their stability could have dangerous consequences for regular matters. How strange matter forms. Strange matter is believed to form in environments with extreme pressure and density, such as in the cores of neutron stars. When a massive star undergoes a supernova, it leaves behind a dense core where gravity compresses matter to incredible densities. If this pressure is strong enough, it could cause the neutrons inside the star to break apart into their component quarks, potentially giving rise to strange matter. Another possible formation process for strange matter involves colliding neutron stars or high-energy events like gamma-ray bursts. These cosmic collisions could produce the intense pressures necessary to kickstart the creation of strange quark matter. If strange matter does form in one of these events, it could theoretically seed the transformation of other stars and planets into strange matter, a scenario that has profound implications for the universe's safety. Strange matter is thought to form in environments with extreme pressure and density, such as the cores of neutron stars or in high-energy cosmic collisions. Once formed, it could trigger a chain reaction in regular matter. The Strangelet hypothesis: a universe-changing threat? The concept of strangelets introduces an even more alarming dimension to the strange star theory. Strangelets are small, stable clumps of strange matter that could break off from strange stars or be formed during high-energy events like neutron star collisions. The danger of strangelets lies in their potential to convert regular matter into strange matter. Imagine a strangelet hitting a planet or a star. Upon contact, it could start converting the atomic nuclei in that body into strange quark matter, leading to a catastrophic chain reaction. In theory, if a strangelet collided with Earth, it could transform the entire planet into strange matter, effectively turning it into a strange star. While this scenario sounds like the plot of a science fiction movie, it's taken seriously by some astrophysicists. Theoretically, strangelets could be formed and ejected from strange stars and travel through space, representing a sort of cosmic doomsday seed capable of obliterating everything they encounter. Strangelets, hypothetical clumps of strange matter, could convert regular matter into strange matter, potentially triggering catastrophic chain reactions. While unlikely, they represent a potential universe-altering threat. Could strange stars exist? The existence of strange stars remains purely theoretical, but the idea is grounded in the physics of quarks and the extreme conditions found in compact stars. Some models of neutron stars suggest that the pressures inside their cores could be sufficient to create strange quark matter, while other models suggest that neutron stars are too stable for this process to occur naturally. There is also the possibility that strange stars are only formed in the most extreme environments, such as during the collision of neutron stars or in the early universe. If this is the case, then strange stars could be rare, existing in only a handful of locations in the universe. On the other hand, if strange matter is as stable as some theories suggest, strange stars could be much more common than we realize, hiding in plain sight among the neutron stars we've already detected. While strange stars are theoretically possible, their existence has not been confirmed. They could be rare objects formed under extreme conditions or more common than we think, hidden among known neutron stars. The implications of strange stars. The discovery of strange stars would fundamentally alter our understanding of the universe. If strange matter is real, it would represent a new and more stable phase of matter that could have profound implications for the study of particle physics and astrophysics. It could force scientists to rethink their models of neutron stars, black holes, and the behavior of matter under extreme conditions. On a more speculative note, the strange matter could have practical applications if it can be harnessed, although the dangers of such an endeavor would be monumental. The conversion of regular matter into strange matter could be catastrophic on a planetary scale, but it might also offer incredible energy yields. However, the risks of experimenting with something as unstable as strange matter would be immense. The confirmation of strange stars would revolutionize physics and offer new insights into the behavior of matter under extreme conditions, although their potential dangers would require caution in any future exploration. If you found value in this video, please give it a thumbs up, like and subscribe to support this channel. Please share across social media platforms to reach a wider audience. Are strange stars the most dangerous objects in the universe? Strange stars, with their potential to convert regular matter into strange matter, could indeed be among the most dangerous objects in the universe, if they exist. The very idea that a small clump of strange matter could trigger a chain reaction powerful enough to destroy entire planets is both fascinating and terrifying. While strange stars remain theoretical for now, their study pushes the boundaries of what we know about the universe and the limits of physics itself. At the heart of this inquiry is the search for understanding about the nature of matter and the ultimate forces at play in the cosmos. Whether or not strange stars exist, they represent the cutting edge of astrophysics, highlighting the vast unknowns that still await discovery in the universe. Detecting strange stars is a challenging task due to their theoretical nature and the fact that they are expected to look quite similar to neutron stars. However, several potential methods have been proposed to identify these exotic objects. Below are some key approaches that scientists could use to detect strange stars. 1. Gravitational wave signatures. Gravitational waves are ripples in spacetime produced by extreme cosmic events, such as the collision of compact objects like neutron stars or black holes. If strange stars exist and collide with other strange stars, neutron stars, or black holes, they would produce unique gravitational wave signals. Why it matters. A strange star is denser and more compact than a neutron star, meaning the gravitational waves emitted during their collision would have different frequencies and patterns. How to detect. Observatories like LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo are designed to pick up these signals. A peculiar signature in a gravitational wave could suggest the presence of a strange star. 2. Mass-radius relationship. One of the distinctive features of a strange star is its mass-to-radius ratio. Strange stars are expected to be smaller and denser than neutron stars of similar mass due to the extreme density of strange quark matter. By measuring the mass and radius of compact stars, astrophysicists can look for anomalies that might indicate the presence of a strange star. Why it matters. If a compact object has an unusually small radius but a high mass, it could be a strange star rather than a neutron star. How to detect. This can be done by observing the X-ray emissions from these stars, which can be used to estimate their size and mass through techniques like X-ray spectroscopy. 3. Gamma-ray bursts, GRBs. Gamma-ray bursts are extremely energetic explosions that are often linked to the collision of neutron stars or the collapse of massive stars. If strange stars are involved in these high-energy events, they could produce distinct gamma-ray signals, especially if the collision converts regular neutron stars into strange stars. Why it matters. If strange stars are formed during these events, the gamma-ray burst could have unique characteristics, such as unusually high energy or a specific afterglow pattern. How to detect. Satellites like NASA's Swift and Fermi gamma-ray space telescopes are equipped to observe gamma-ray bursts, potentially providing clues about the involvement of strange matter. 4. Thermal emissions and cooling rates. Strange stars might have different thermal properties compared to neutron stars. The cooling rates of strange stars could be slower due to the unique properties of strange quark matter. These differences in thermal emissions could be a way to distinguish strange stars from neutron stars. Why it matters. Neutron stars cool relatively quickly over time due to the release of neutrinos. If a compact object cools at a slower rate, it could indicate the presence of strange quark matter. How to detect. Astronomers could measure the thermal X-ray emissions from compact stars over time, looking for deviations from the expected cooling patterns of neutron stars. 5. Strangelets in cosmic rays. Strangelets are hypothetical small chunks of strange matter that might break off from strange stars or be formed in high-energy cosmic events. These particles could travel through space and potentially reach Earth, where they could be detected as part of cosmic rays. Why it matters. Detecting strangelets would provide direct evidence of the existence of strange quark matter and, by extension, strange stars. How to detect. Experiments such as the Alpha Magnetic Spectrometer, AMS, aboard the International Space Station are designed to study cosmic rays and could detect strangelets if they exist. 6. Pulsar timing and glitches. Strange stars could behave differently from neutron stars in terms of their rotational dynamics. Neutron stars often experience glitches, which are sudden changes in their rotational speed. These glitches occur because of the internal structure of the neutron star. If strange stars experience glitches, they could have different patterns or magnitudes compared to neutron stars. Why it matters. A difference in the frequency or intensity of glitches could hint at an underlying strange star rather than a neutron star. How to detect. Radio telescopes that monitor pulsars, rotating neutron stars, can measure these glitches with extreme precision. Anomalous behavior in pulsar timing could be a clue pointing to the presence of a strange star. 7. Electromagnetic emissions from star quakes. Similar to glitches, strange stars might experience starquakes due to their internal structure. The resulting electromagnetic emissions from these quakes could have different characteristics than those from neutron stars. Why it matters. Starquakes on strange stars would release energy in the form of X-rays or gamma rays, but the pattern of emissions could be different due to the strange quark matter inside. How to detect. X-ray and gamma-ray observatories could capture the emissions from these starquakes, providing indirect evidence of strange stars. 8. Rotational instabilities. Strange stars might exhibit unusual rotational dynamics because of their extreme density and compact size. As they spin, they could develop instabilities that would affect their rotational speed or produce irregularities in their magnetic field. Why it matters. Neutron stars are relatively well understood in terms of their rotation, and any deviation from these expected dynamics could indicate the presence of a strange star. How to detect. Monitoring the rotational period of pulsars or other compact objects using radio and optical telescopes could reveal rotational instabilities unique to strange stars. While detecting strange stars remains a theoretical challenge, advancements in astronomical observation tools, such as gravitational wave detectors, X-ray and gamma-ray telescopes, and cosmic ray detectors, offer promising methods. By identifying anomalies in mass, radius, cooling rates, or gravitational wave signatures, astrophysicists hope to confirm the existence of strange stars and further unravel the mysteries of the universe's most extreme objects. If you enjoy this video, please give it a thumbs up, like and subscribe to our channel for more self-improvement videos. Comment below to tell us how useful you found this video. Remember to share on various social media platforms to reach a wider audience. Click the notification bell to get notified anytime we post a new video. Thanks for watching, see you in the next video.